So now we are going to start module 8, earthing calculation. And earthing is most disputed topic and even the most important topic. And when we go at the site for any electrical installations, particularly for the substations, then along with the foundation, the first drawing that required at the site, the first material that required at the site, that is the earthing conductor and earthing drawing they required, first of all, because along with the equipment foundations they also wanted to do the earth met below the ground. So earthing is the first drawing that required at the site along with the layout plan and section document. Yeah, so for the drawing, for the site pointer, this is important. First we have to send this drawing. And earthing is most like a disputed topic, and everyone have their own perception about the earthing. And earthing is common not only for the subsistence, this is very common topic, and everyone have their own knowledge, own perception on the earthing. So we'll take your point of view also, whatever you're learning, what is your understanding about the earthing, that also we will consider and we will include, and we will do some add-on on that concept, right? So yeah, let me like quickly ask, like, what is the difference between earthing and grounding? These two words we hear when we talk about the earthing. Yeah, anyone can unmute who do not have the noise in the background. They can put their idea about this.
Hello.
Yeah.
Hello, sir. This is Sanket.
Yeah, Sankit.
So, as per my understanding, normally the term earthing we use whenever we do the system earthing, and the term grounding is generally used like for neutral bushing or for even DC circuits also sometimes. This
Okay.
is the perception amongst the
So
means
as per your so far
but as
understanding,
but
as
so far understanding, this is the common perception actually, but both are same.
both are same, and
Is my understanding.
the difference is what? The neutral bushing.
Normal perception is whenever that both are same, but whenever we do the system earthing, that
Mm-hmm.
is thing, then the term is used as earthing.
Mm-hmm.
We do some neutral grounding or means neutral earthing or connecting the neutral bushing to the grounding or something like that.
Mm-hmm.
Then in that case we call that as an earthing grounding.
Mm-hmm.
And times in DC circuits also this grounding term is normally used and earthing is.
Yeah, correct. So
But in actual practice, if we look closely, then both are same. This is as per my understanding.
yes, so your understanding is correct as per the standard also, as per the IEC and IEEE standard, as per the regulations also. First of all, the earthing E and the grounding G, both are same. There is no any statement found in the standard who are telling that both are the different. Only the difference is what? The difference, like in the European country, they say the earthing. The American country, they say grounding. That is the difference, just like the Atlantic Sagar.
Yes, sir. I forgot to mention this also. Yes, that's right.
Yeah.
Uh, that's right.
So this is the difference between earthing and grounding. This is the point number one that we discussed, that both earthing and grounding is the same. Only the country is convention, like European country follow the earthing, the American country follow the grounding. And second, we can say what the in generally, as per the practice, we understood, or we used to say that when we connect any transformer on any equipment, suppose we are taking the transformer, and here we have the R phase, Y phase, and B phase, and neutral bushing, and here we have the outer enclosure of the transformer. So when we do the connection of the outer enclosure of the equipment, and that is the non-current carrying part, to the earth, when we connect, then we call this connection as the earthing. And whenever we connect the current carrying part of the transformer that may carry the unbalanced current to the earth, then this type of the earthing we refer as the grounding. So that is the grounding, and this is the earthing. So what we understood here, and that is the correct understanding. If anyone have the any other perception, they please correct. earthing and grounding both are same. Only the difference is the country. European earthing, American grounding. And the difference, if we say, this is the minor difference, but non-current carrying part to the ground, this is we used to say earthing. And when we connect the neutral bushing to the ground, then we say this is the grounding. This is the one we can say. If any minor difference, then this is the minor difference with respect to the equipment earthing. This we can say like this. So what we conclude and what we decided here, that both are the same, country difference, and this is the one example for the earthing and grounding. Now the next, that
Excuse me,
why.
sir.
Yeah.
Sir, this is Abhinav.
Yeah, I mean,
I would like to add some points here.
yeah.
Please correct me if I'm wrong. As you correctly said, that earthing is basically connecting a non-current carrying part or body of a machinery with the ground or earth. So this is what earthing is. Secondly, grounding, for my opinion, in my case, what I think is grounding basically we refer when some sort of fault occurs. For example,
Yeah.
if any machinery or panel or motors,
Mhm.
if there is leakage current happening
Yeah.
or some sort of unwanted other
Unbalanced.
type of fault happens, then
Yes.
we refer it as a grounded or earth leakage ground, some sort of things,
Correct.
or neutral ground resistance. As you said, in case of transformer, we connect a
Mhm.
resistor of value, some optimum value with the neutral point. So
Hmm.
grounding basically refers to unwanted things like fault or leakage current
Or unbalanced also you can add.
or unbalanced. Yes, of course, unbalanced things. And earthing, in my perception, is connecting solidly earth, keeping resistance minimum possible,
Yeah,
or
correct.
most of
And
the
that
cases
is
it is less than
that
1 ohm.
you can add, that is less than 1 ohm.
Yeah, yeah.
We try to keep, and we try to keep this also less than 1 ohm, but that minimum to minimum resistance we try to target to keep less than 1 ohm, or as much as low possible. Yeah, your perception is correct. That is the your understanding is correct. That is perfect. Okay. Yeah. Any other who have their own experience about this, they can like share their experience.
Sir, this is Srinivasan.
Yes, sir.
Sir, so I understood grounding means only unbalanced current is correct?
Yes. Neutral.
Okay.
Neutral.
Okay.
Neutral bushing connect with the earth, we can say grounding. And if you know that we use the NGR and we say the NGR refers the neutral grounding resistance, right?
Yes, agree, sir. This is a earthing. We are using solid earthing. Okay, this NGR you are using neutral side. Yes, agree, sir.
Yeah. Okay. So
Both
now,
are similar. Both are similar words in as per standards. Huh?
yeah, as per standard, both are the same.
Okay, agree, sir.
Both are the same. And this is like what happens in Europe. They follow their own currency. In America they follow their own currency. So this is the difference of the country. And as you know that that globally there is two standard we follow. One is the IEC standard, and second is the IEEE standard. The IEC standard comes from the European, right? This is the European country standard, and the IEEE standard comes from the US. Correct? US, Canada,
Yes, correct.
these are the IEEE country. European plus Asia also influenced by with this Europe. So here also we follow the IC standard in a similar way. As IC comes from the Europe, IEEE comes from the America. Similar way, earthings, IC or European countries say this earthing, the American countries say as the grounding. That is the
But
country.
yes, sir. But
But
sometimes we are using here main earthing and neutral earthing.
okay,
This words we are using.
both are same. Both are same.
Yes,
Srinivasan,
yes, sir.
both are same.
Main
Okay.
earthing means is connected to system.
Yes, yes,
Neutral earthing means is connected to neutral
yes.
point.
Neutral point. Yeah. And technically, as per the IC, as per the standard regulations, both is the same.
Also, testing time we cannot do the test neutral grounds, sir. Only we are doing main earthing.
Yeah, correct. Main earthing test. Correct. Yeah. Okay, Srinivasan. So let us understood one more point, that what is the earthing? What is the earthing? As we discuss Similarly, what is the earthing? Earthing means we can define earthing in a very simple language, that as we know that equipment is already placed on the earth right now. This is equipment foundation, and on this we have placed the equipment. Suppose I'm taking any motor, so this is already placed on the earth. So what is meaning of the earthing? To connect the outer metal of any equipment that is placed above the ground via a metal strip. Via a metal strip. This metal strip may be of the copper, maybe of the aluminum, RGI, RGS, of the MS, as per my requirement, as per the client technical specifications. We can select size, we can select based on the fault current. So the connection of the outer metal of equipment that is placed above the ground with help of a metal strip to a metal pit that is placed below the ground. So the metal to metal connection via metal strip, we can say this is the earthing. In any very layman language right now. Am I correct? This very layman language to explain anyone who is not coming from the technical background. What is the earthing? Means connect the outer enclosure metal with a metal strip to a metal pit. That is the earthing. This is we can define in a simple language like this. Now next, why earthing? Before coming on the main calculations, I just wanted to discuss the basic concept about the earthing. As we discuss for each topic, their basic understanding, and thereafter we go on the main calculations. Why earthing? Because sometimes when we go in a general conversation, so these things comes into the general conversations. So that is why we should keep the clear idea about these words in general technical conversations also. And that is the agenda to discuss these points. Yeah. Why earthing required? I can say like this. Anyone have any opinion about this? Why earthing is required?
This is Arva, sir.
Yeah.
Fault current is going to through earthing, sir. If earthing not there, fault current not possible to ground.
Correct. Fault current not possible to ground. Then what will happen?
So it will happen. The current surrounds the equipment. It will happen shock the if and when you touch.
Okay. Then what the next problem? Why not earthing? Okay. I'll take your point and let us understood in an overall view. First of all, suppose this equipment we have placed above the ground. Okay, I understood everyone that for the safety equipment person, these all is the reply that is okay. But let us understood some other point also. Suppose this equipment we are placed above the ground here, and as we know that any electrical equipment have the inner conductor, then insulation, and then outer enclosure. Suppose what will happen, this insulation due to the aging period or due to the weak insulation material, this insulation fail, then this current will flow on the outer enclosure. If we have not done this earthing, then what will happen? The potential of this outer enclosure of equipment will rise, and since this fault happens inside the equipment that cannot seen outside by any O&M engineer, they could not see this fault happens inside the equipment, and if they are touching this equipment, then due to the higher potential of this equipment, the current may flow through the body, and there might be a case of the electrical shock here. So to avoid these conditions, for the safety of the person, because here the equipment have been faulted, I'm not going to do any equipment protection. I'm going to do for the person, for the human being protections. We do the equipment earthing. So this is the point number one, that why we are doing the earthing. Second point, if let me take one technical example for the system earthing. This is the equipment earthing. I will come on the type of the earthing just after this discussion. Here I have main bus bar, then here I have circuit breaker, then thereafter we have one transformer, that is delta here, or let me take the star in a star winding here, and then here we have the LV, and this here we have the bus LV side bus. Suppose I have not done this neutral point to earth, I have not done this. So what will happen? if I have not done any neutral earthing or system earthing, we can say, if neutral is not earth, n is not earth, then what will be the effect on the system? First of all, if any line to ground fault happened, this line to ground fault cannot be, fault is there fault is there, but it cannot be sensed. Why it cannot be sensed? Because there is no any return path for this fault current. So the point number the problem number one, this is the problem number one, I can say here. The problem number two, that the ground fault, I again repeat, the ground fault cannot sense. Second problem, what will happen, that since this is the star connections, so in the star connections we know that the on the phase the voltage will come, that is the line voltage, line to line voltage divided by root 3. This will be the phase voltage. Suppose this is 33 by 11 kilovoltage transformer. So on this, on any phase the voltage will come, that will be the 11 kilovoltage divided by root 3. I think this will come around 6.5 this kilovoltage. But if system is not earth, so at the time of the fault, the phase voltage will jump to the line voltage. The phase voltage will jump to the line voltage. Then what will happen, since the equipment, this phase insulation is designed is designed for the phase voltage, but if the voltage at the event of the fault jump to the line voltage, then this insulation will break down due to the higher voltage. That is the line voltage. I mean to say, if equipment I have designed this insulation for 6.5 kilovoltage, and on that this is 11 kilovoltage is coming, then we could not sense the fault. Second, the equipment going to fail, the insulation going to fail due to the higher voltage stress. So what is the problem? If system is ungrounded, three problem we understood here. One, equipment, the person is not safe. Second problem, we understood the line to ground fault cannot sense. Third, the phase voltage will jump to the line voltage if system is not grounded and system is not earth. So this is the disadvantage. Now one very important point, that what about if there is no line to ground fault, if there is three-phase fault, then what about the three-phase fault? We can sense this three-phase fault or not? Yeah, I need like any yes or no, whatever you feel right, whatever as per your understanding.
Sir, if in case in at the place of line to ground fault, if three-phase fault occurs, then definitely the incomer feeder, means 33 kV feeder, I mean bus bar, will definitely sense it, no matter whether earthing has been done in the transformer or not.
Correct. So what
I guess this is what
yeah,
you
yeah,
are
correct,
asking.
correct. Let us understand this very important statement, this very important point. The point is that all the earthing, all the grounding is not for the three-phase fault. I again repeat, all the earthing, all the grounding, whatever we are discussing or we are going to discuss, that is not for the three-phase fault. Three-phase fault, no link for the earthing and grounding. All the earthing and grounding is linked for the ground fault of are the, and since out of all type of the fault, triple L, triple LG, double L, and single L2G, all this we know the type of the fault, right? The three phase triple L type fault. We have understood it during the our engineering time, right? Triple LG type of the fault, double L and L2G. Like this is the type of the fault that happen in the electrical power system. So the probability of fault of triple L is very less. This is also very less. Most type of the fault, around 85% of the fault is that L2G fault. So all the system is designed for the L2G fault because all the earthing, because the probability of fault is higher. And if three phase fault, earthing and grounding will not going to impact anything here.
So basically, whenever there is an unbalancing, neutral shift will occur, and that will cause a neutral potential non-zero.
Yeah.
And that is why earthing is needed or must.
Yes, needed. And if this three phase fault, three-phase symmetrical fault, right? Now, because the three-phase fault, we say the symmetrical fault, right? As we can divide the fault in two type again, symmetrical and unsymmetrical fault or asymmetrical fault. This is the symmetrical faults. It comes into the symmetrical fault. This comes into the asymmetrical fault category. So if this kind of fault, earthing grounding is not going to play any role here. Grounding not going to play here role. What the earthing can play? Earthing like only this is for the equipment protect human protection. Yes, we can do that, but any neutral grounding is not playing any role in that. So
Yes.
two important point we discussed here. The first, what is the difference between earthing and grounding? The conclusion is that both is same. The difference is this, the conventional that we used to say, but technically is same. Now we discuss here what is the earthing that we discussed. Third point we conclude and we discussed here that this if system is ungrounded, so what is the problem that we can say? Human is not safe here, and here equipment is not safe, and the line to ground fault we cannot sense, and the phase voltage will jump to the line voltage. This earthing, what is the role of this earthing? If we do the earthing of this star point to the ground, then this earthing provide a return path. This earthing provide a return path. This fault current, whatever coming, it will, because the ground is common, it will go reverse back here. Now what I will do, I'll put the CT here that we refer as the NCT, neutral current transformer. This NCT will sense the current. It will sense the current. It will give output to one earth fault relay. We in switchyard we use the REF relay, the restrictive earth fault relay, and REF relay will sense and it will give tripping command to the associated breaker. Right? This is how we are. If we done the earthing, then how we can do the protection of this equipment. So the system earthing, the neutral earthing is for the equipment protections, and the earthing of outer enclosure of the body, that is for the human protection. That is not for the equipment protection. That is only for the human being protection. This is for the equipment self protection. Neutral provide the return path. Now you can ask me that what should be the NCT rating here in that case. How we decide the NCT rating in that case, right? The general practice that we can decide the NCT current ratio, we can take that how much current is flowing on the phase side when there is no any fault happens, and this NCT rating, in this NCT rating, we can select same as the phase CT. If this is 600 bar 1, this is the, we can also take the 600 bar 1 CT here also. This is how we can decide the NCT rating. Okay, so this three point we discussed here: earthing, grounding. What is the earthing? Why earthing is required, and what is the drawback of the ungrounded system? Let me take it up if it is possible. We can
I
simply,
have a doubt. Excuse me, please.
yeah.
Sir, as you said that NCT rating, I mean the CT rating is same as that of phase CT ratio.
Yeah,
So is it a convention or is there any calculation behind? I
both
don't
we
know
can do.
actually.
Both. This is the convention that we are telling. Yeah,
Okay.
this convention. Yeah, but when you go on the calculations, because you should know the fault current right now. What is the fault current is coming? So what I can sense that I can put the NCT same as the phase CT, because here if I go to the REF, then we do the matching of the phase CT and the NCT, and we do the current subtraction here, and then we give this output current to the REF that we'll cover in the protection part. So that is also we take this NCT similar as the REF phase CT if we are doing the high impedance type protection in that case. And this is the convention that we take NCT as the phase CT. This is the convention also. Okay, Abhinav?
But Raghav, this is Kamesh.
Yeah.
Can you just go to the diagram once again, please?
Okay. Oh.
The drawing which you showed, or probably
Since actually today we are coming on the earthing, so I'm not going to stress this point, but yeah, I can take for you. This
okay, yeah, just you mentioned about the neutral neutral CT, right?
Yeah.
But you might have a covalent CT upstream. I mean, you usually have a covalent CT on the upstream, and when you are selecting a covalent CT, so if you go up, yeah, there, you will have a covalent CT. If you have a covalent CT, which is again doing this unbalance,
Mhm.
and you have a return path, the co-balance city can detect. And while I mean, what you said is correct. I'm not saying. I'm just adding a point that you usually our systems which I worked on, we have a core balance city fitted there for the upstream,
Mhm.
and
Correct. Your point is
they are quite. The ratio is like 50.
50 by
If
1
you
ampere, right?
mentioned about 600,
Yeah. This
yeah,
50 by 1.
something like
For
that. So
CBCT, we take 50 by 1. Yeah.
something like that. I'm just adding a
Yeah, your
point.
point is correct. Point is correct. That also. I'm telling this example now. This is what example.
Yeah.
Not emphasizing calculus. Yeah. Okay. So now coming back to the agenda of today. This is the in general discussion. So let us start this earthing module. Now, what is the content that we will discuss under this module? What we are going to discuss, what is mean by earthing, that is done. Then why earthing required and difference between earth and non-earth system, this is also we discussed now. Tolerable body current, yeah, that is also very important and interesting topic. How much current a human body can tolerate? Yeah. Yes, I'm just waiting any reply if anyone aware about this concept that how much current a human body can tolerate.
Your if you reach 1 amp, person will chances to die, sir.
Yeah, 25 milliampere, 30 milliampere.
You
Okay.
reach 1 amp, sir. If you reach 1 amp,
1 ampere.
1 ampere.
Oh, you can
One to one to
tolerate 1 ampere.
one to yeah. What?
Okay. So let let us avoid this all confusion. 1 ampere, 30 milliampere, 25 milliampere, 30 milliampere. Everyone have their own reply. 10 milliampere for AC. Okay, let me ask one more interesting question. Which is dangerous, AC or DC? Next point. Which is more dangerous, AC dangerous or DC dangerous?
DC danger.
DC, right?
Yes, DC danger.
That is what we study in college time, but that is not correct. Your point, your understanding, your reply is correct as per our academic. DC is dangerous. Okay. And also, I also know that DC is dangerous. But what is the reference? Who is telling this is dangerous? You can say that, okay, AC comes on 0 point, but DC not comes 0. So DC is straight. So DC is dangerous. But what is the reference of that statement? What is the reference stand for that statement? Let me take these two questions. That how much body current and whether AC dangerous and DC dangerous. Okay, so as per the standard. Now I will refer the standard. Okay, now I will not, because I cannot say my own statement. We'll refer the standard, and for this earthing, for the earthing, for the earthing, there is main standard that we follow across the world, that is the IEEE at T. This is the main standard that we follow, IEEE at T, that I will share with all of you. This standard is having the 200 page, so no need to read 200 over page, all page, because even though again this is very tough and time consuming, I will tell you the relevant page that we should know at least minimum. And if you have time, you can go all 200 page, but I'll tell you the what is the main important page that we should go, that we should study at least. Yeah. So let me go to this standard. This step I will take as per the simulation tool. Now earthing, where is the earthing? Earthing. standard. Where is that standard? Yeah, this is IEEE standard. Yeah. So in this standard, yeah, first of all, let us discuss that how much current we can tolerate. Please come on the clause 5. This range of tolerable current. Clause 5 IEEE 82000 page number 11. And if we check this standard, what is the range of tolerable current? What is given here in this standard? Effect of frequency. Yeah, frequency also they have link here. And what is the okay? This I will take. This I will take later on. Let me come on the body current first, or tolerable body current. Yeah, tolerable body current. Tolerable body current limit. Okay, duration of formula 50 years. Let us take. And when we talk about the current, then two things involved. When I ask you that how much current, how much a current a human body can tolerate, then you should ask two things from me. That for what is the weight, what is the reference weight of the human body, and for how much duration, right? For 50 years. And you can ask me that what is the frequency. Let us take 50 years now. So weight, there is two weight that we take conventionally as per the standard. That is, one is the 50 kg weight and second is the 70 kg weight. And durations, we can take 1 second, or we can take the different seconds also. So this two matter is important. Based on this two reference, we check the current. So if my body weight is 50 kg, let me check this statement. Person weighing approximately 50 kg, right? The value of IB is the body current, tolerable body current, that is 0.2116 under root of TS for 50 kg body weight. What I mean to say, if my shock duration is 1 second, in that case, a body having 50 kg weight can carry the 1116 milliampere or 116 milliampere, 1116 ampere, or we can say the 116 milliampere. This is the statement. Hope this point is clear. Now you can revise, you can remember lifetime, right? No need to guess anything 30, 51, whatever. Yeah, you can, as per this standard, I'm telling again. Okay, as per this standard, that is why I'm not coming on my PPT. I'm telling with reference to the standard only. And if body weight is 30 kg, yes, at 70 kg, in that case, they have also mentioned, yeah, here alternate assumption. If the body weight is 70 kg, then the person can tolerate 157 milliampere. This is the two statement that I have delivered here. Same I have took from the standard in my PPT. Okay, this point all is we have already discussed. Coming on tolerable body current, first of all we should know that whether the current kills the voltage kills human body. Yeah, current kills the human body, not the volt. This we should also know. And how much current how much current is 50 kg. This is the page I have taken. Here, and this is statement. We can deliver that a 50 kg person for the 1 second duration can tolerate 116 milliampere. 70 kg person for 1 second can tolerate 157 milliampere. Now you have the reference standard for this. that what is the reference standard. And now you have the formula also. Based on that formula, you can also calculate if the second is 0.5, then what should be the tolerable current right now. The same formula that we have seen in this IEEE. Under root TS, so in place of 1, you can put 0.5. This you can calculate the tolerable body current for the different time durations also. Hope this point is clear. Hope this statement is clear that how much current a person having 50 kg or 70 kg weight for 1 second they can tolerate, and how it depends with the different time durations. If clear, please let me know so that I can move to the next topic. Yeah, this is the statement that I have derived, that I have taken from the IEEE. Is it fine? Just waiting for your response here. You please be active on the chat box. Okay, next, as we discussed that whether AC is dangerous and DC is dangerous. So let us again take the IEEE and range of tolerable current, effect of frequency, and in the effect of frequency 50 and 60 Hz, and they have one statement here. The research indicates that a human body can tolerate a slightly higher than 25 Hz current, higher current, slightly higher 25 Hz current, and approximately 5 times higher DC current. 5 times higher DC current. This is the statement that I can. 5 times higher DC current. This standard is telling that as per the research, they are telling not as per the calculations, that person can tolerate 5 times higher DC current. They mean to say that AC is more dangerous, DC is less, and you can tolerate 5 times more DC current. For the 50 or 60 years, they are comparing with this frequency. Yeah, that breaking your concept, I hope. For the same, they have taken the effect of frequency. They are telling the humans are very vulnerable to the effect of electric current at frequency of 50 and 60 Hz. Currents of approximately 0.1 ampere can be lethal. Okay, research indicate that a human body can tolerate slightly higher 25 Hz current. They are telling that if your frequency is less 25 Hz, you can slightly higher current body can tolerate, and approximately 5 times higher DC current. At frequency 3000 to 10,000 Hz, even higher current can be tolerable. Now they are telling if frequency is 3 to 10,000, even higher current can be tolerable. They are telling some scientists name here. Okay, in some cases the human body is able to tolerate very high current due to the lightning surges. The International Electrocommission Technical provide the curve for the tolerable body current as a function of frequency and for the capacitive discharge current. This is the standard for that. Other studies of the effect of both direct and auxiliary impulse current are reported in this. So as per this standard, I'm just reading this standard. This is a statement. I'm not telling who is wrong, who is correct. I'm just reading this statement, and this is the statement here. So I think we have some additional information as per the standard. Okay. So two things here we discussed. If we conclude that a person can tolerate 116 milliampere for 1 second, 157 milliampere for 1 second as per the IEEE standard 80, right? And a DC current is more dangerous, like the AC current is more dangerous than DC current. A person can tolerate 5 times more DC current compared to the AC current. This is what written in this standard. Yeah. Am I okay? Can I move to the next topic? Okay, so next is what is the type of the earthing? This all I am discussing general technical conversation that we usually do. This is all is that, not coming on the syllabus. This is the not part of the syllabus. The general basic background of. Now let us discuss the type of the earthing. Yeah, as we have discussed in the beginning, that there is two type of the earthing we do. One is the equipment earthing. One is the equipment earthing, as we have discussed, and second is the system earthing. Equipment earthing and the system earthing. So equipment earthing for what? For why? This equipment earthing for the equipment protection, or we can say system earthing, or I can say here equipment ground, system grounding. This will be more relevant. System grounding, equipment earthing. So equipment earthing, this is not for the equipment protection at all. This equipment earthing is for the human protection. This is for a person protection. This is for the human body protection, not for the human equipment protections. Human body protections. When it comes to the system earthing or system grounding, this is used for the equipment protection. And how it protects equipment protection, we have seen in the beginning, right? That how it provides the protections. This we have seen in the beginning here. System grounding and equipment earthing. So earthing we can divide in two parts. And as we discussed in the beginning, that the non-current carrying part, if we do with the earth, then we call it the equipment earthing. And if we connect the neutral of the generator or the transformer to the grounding, then we call it the system earthing or system grounding. So earthing is two types. This is then conclusion. Type of the earthing, there are two type of the earthing. As first is equipment earthing and second is the system earthing. The equipment earthing for human body protections, the system earthing for equipment self protection. The neutral point of generator or transformer is connected to the ground. This is the meaning of the system earthing. That we have taken this side picture. This is my earthing grid. Here we have connected the equipment to the grid, then this is called the equipment earthing. And in this case, we have taken the neutral bushing of the transformer and that we connect with the grid. This is called as the system earthing. At the side, this look like this. This is my neutral bushing of the transformer that we have taken here. And on the neutral bushing of the transformer, here we have the clamp and connector. And this is, I'm doing the connection, help of the earthing is grid to the ground. This is the case. This earthing we called as the system earthing or system grounding, we can say. So earthing is two types: equipment earthing and system earthing, right? This is what we discussed. Now the next, if we do the earthing, so what type of the fault current we are taking? The selection of the fault current for the grounding. The three-phase triple L fault current not depends on grounding or ungrounded system, and also not depends on any type of the system grounding or neutral grounding. The three-phase fault current value will be same whether the system is grounded or system is ungrounded or any type of the neutral grounding. We are not in the grounding, we are not taking the three-phase fault current. We are taking the line to ground fault current because that is going through this grounding to the earthing strip to the ground. So we are taking the line to ground fault current. This we can understand by one example. Let me take some E-type example. Here we have developed some cases. So let us take the service in. Yeah, this, let me change this one. Yes, and I think one case we can also take. The first of all, let me take this service out and this case also service out. Okay, let me take one case like this one and let me convert this transformer primary delta, secondary star winding, and grounding is solid grounding. Let me take the open grounding. Means grounding is open. means ungrounded system. Click on the OK. Here system is ungrounded. Now this is my short circuit analysis. This tab is for this. If I take this tab, here is the result, that what kind of the current we wanted to do the simulations. Let me take the run three phase device duty. If I run this, what will happen? Let us see here. Yeah. If three phase fault current, system is ungrounded, the value is coming here 6.57 kiloampere. Right. Now let me take another example. Let me take the 60909. Let me go with the L2G fault. Now let me change the type of the fault. Yeah. Yes. Three phase that we already have seen. Now fault type L2G. I am taking the display short circuit current fault type. These are the fault type as we know. Now I have taken the line to ground fault type. Click on the OK. Yes. The value is 0 kiloampere. What you observe next point here, that initially when it was the three phase fault, let me again do the three phase fault current and let us compare both the cases. Three phase fault current, click on the OK. Yes, this is my current and this is my voltage, that is 11 kilo voltage. Three phase fault current is coming here 7.43 kiloampere. If system is ungrounded, then also this current is coming, but voltage is 11 kilo voltage. Right, let me take the snip of this case. I have taken the ungrounded system. I just wanted to show you that in the ungrounded system, my delta here is star and star is not grounded. If I run the three phase fault duty, this fault current is coming and this is three phase fault current. So fault current is coming. What is the disadvantage? This is red because my phase voltage jump to the line voltage, that is 11 kilo voltage, because this is my 11 kilo voltage here, 11 kilo voltage this here we have. So on this the voltage should be 11 divided by root 3, right? That as per the calculations, this should be 11 divided by root 3 and that will come 1.732. This will come 6.5, around 6.4. This should be around 6.4, but this is jumped to the 11 kilo voltage. But yeah, fault current is coming here. So this is the drawback of the ungrounded system. The voltage jump, the phase voltage jump to the line voltage. But yes, a system is grounded or ungrounded, three phase fault current remain three phase fault current. It's not going to change any value. Now next, let us take, if I convert this into the line to ground fault current L2G, yeah, here what we can see, fault current 0 kiloampere. So fault current 0 kiloampere. What I am doing, since the fault happened due to the line to ground, we have taken fault happened but it could not sense. It is showing 0 kiloampere. So how we can sense the fault current here? We have to provide the earthing. So now what we can do here, and this 11 kilovolt is coming again. What I do here, I again go to the transformer, grounding tab. Here let me take solid grounding. I'll go to the other grounding also one by one. Let me go solid grounding. Now here we have done. Now if we do the fault current analysis and 60909, that is the stand for the earthing. L2G already we have selected here. Now in that case you can see this current is coming. Initially it was 0 kiloampere, but now it is coming 7.26 kiloampere, right? So with help of the grounding, what we can see that this current we can now sense. So all the earthing, like all the grounding, if we are doing for the neutral, so that is only to sense the ground fault current, down the three phase fault current. I hope this statement is clear to everyone. Yeah, if clear, then please let me know. And I'll share you one of my project experience that I was doing that project in Sri Lanka. Sector Electricity Board is that country board there, and their soil resistivity was very high. That is more than more. It is coming around than 1000 ohm meter, the soil resistivity. And when we taken the three-phase fault current, then we are not able to meet out the tolerable step and touch potential. It was coming very challenging at that site. So how we achieve, like how we done the earthing in that substations, in place of three-phase fault current, we have taken the line to ground fault current only for the entire earthing calculations. So we done this ETAP study. We have not taken the total fault current. We have taken only line to ground fault current, and that current only we have used for the entire grounding or entire earthing calculations. Uh, this we have taken due to the higher ground resistivity. Generally, we do not take line to ground. Generally, we take the most highest fault that we take, that how much highest fault may come on the system, and based on that we design the system. But at that site it was the challenge due to the highest resistivity. That's why we go with this kind of the alternation, that we consider only line to ground fault current for that thing. So like why I'm sharing this example, that when you face this kind of issue, you can go with the line to ground fault current in the entire thing system calculations.
Sorry for disturbance, Raghavan sir.
Yeah.
Sir, this ETAP calculations, how we know well managed? Because you are telling okay well, but we don't know any practice.
See
You are
how
telling
you will do the day
calculating.
one, yeah. That is why I'm here, na.
Uh, yes, sir. But you are telling okay, we understood, but
And don't
physically,
worry, we have module. Yeah, ETAP we have dedicated chapters now.
yes, yes.
Why
But
we have dedicated module for the ETAP. In that we will study about the ETAP only. But actually, what happens that when I'm delivery any statement, if I do some simulations, you can see the result.
okay,
So this simulation not for the ETAP purpose. This simulation is only to make the concept only.
okay, I agree, sir.
And not how to do the ETAP study and now how to fit all this. This is for that there is a separate topic in the syllabus, that is the ETAP software introduction, how to get a start, create familiar with the ETAP toolbar, modeling, load flow, short circuit. So during this we will discuss about the manual
Okay, sir.
calculations. These all I will calculate manually, and
Okay,
then
okay.
I will run in the ETAP, that the ETAP is telling this one and manually this is coming, so both we can match. But as of now, this I'm referring only to make the concept.
Yes, thank you, sir.
Yes, because both is not possible at the same time right now. One by one we have to go. Yeah, what is the confusion? Tell me. Repeat the statement. What kind of a statement, Deepak?
Sir,
Ah,
you told the ungrounded system and grounded system relation. You said one statement, so I want to write that statement, so I just want to repeat it.
so the ungrounded means here you go here and then do the open, and now system is ungrounded, right? And now if I run any line to ground fault current, so system is ungrounded, so I cannot sense any fault current. It is coming 0 kiloampere. Okay. So system is what is my statement here? If system is ungrounded, then the line to ground fault current we cannot sense, and that is why we have to provide the grounding for the transformer neutral. Okay.
Okay, okay,
And once we provided the grounding here, that we have taken the next second case. In now we have provided the grounding, and then when we are doing this simulation again, now this is coming 7 kiloampere. So this grounding is providing the return path for the fault current, and that we can sense, and we can do the protections here, right? Okay, Deepak.
okay, sir.
and
One more
and
additional.
and don't worry here, for the ETAP now we have dedicated module, so we will do all type of the fault and their effect. Okay.
Okay, sir. One more additional question for this. If we here we use the solid grounding, sir. Is any register like there was a other option also, na, solid
Sorry,
register.
yeah, Deepak, please follow me. I'll coming one by one. I have taken all these
Yes,
things.
yes.
You don't worry.
Okay, okay,
Follow me.
okay, sir.
Follow me. Yeah. So this statement is clear. This is state For this statement only I have done this simulations. My statement is that earthing is not for the triple L fault. Earthing is only for the line to ground fault. That is the statement. And here I have taken the example that this example I have taken the snapshot by doing the ETAP study. I have taken this three cases: case 1, 2, 3, and 4. Case 1 delta star. My slide is visible, so I need to zoom. Please let me know. If it is not visible, I can zoom this. Please let me know. Like you are at the remote end, so my page size is okay, or should I need to zoom for your proper view? Yeah. Now this is okay. Yeah, Chandan. We don't know if this is okay. Yeah.
Yes, sir. Fine, sir.
Okay. Okay. Yes, the case is that we have taken the four cases. Now case 1, we have taken this 33 by 11 kilovoltage transport 10 MVA transfer delta star we have put here, and now we have done the fault current three phase as I done here, three phase, only three phase fault current, right? So when I run the three phase fault current, in that case fault current three phase, if delta star the value is 6.35 particular, it is the value is coming, it is not changing. If I done delta star and star is earth ungrounded, yeah, the grounded system, again the fault current remain the same, 6.358 kilometer, no, nothing any change. If I done the delta star and star with the ngr, here I put the ngr, in that case also we do the simulations, then again result is the same, nothing any change happened in three phase fault. If again delta I have taken here, now I change the vector configuration of the transformer, delta, again the fault current remain the same. So what I understood here, that the three phase fault current, if I change the vector, the winding configurations, if I put the like solid grounding, ngr grounding, delta, the value will be the same, it will not going to change. It is not depending on the transfer winding and vector group. So what depends? All the things that depend on the transfer vector group, that is the line to ground fault. So three phase fault current means your concept is clear, I hope. This is not going to come into the syllabus or into the study. This will be the remain same. Here I have taken the four different examples, right? If I'm putting the ngr, what we understood from here, if I'm putting the ngr, so I'm not limiting the three phase fault current. I hope this is clear. If I'm putting the ngr, I'm not limiting the three phase fault current, right? What I'm limiting, I'm again limiting the line to ground fault current if I'm putting the ngr, not the three phase fault current. And that is the reason I have taken this ngr here. I hope this statement is clear now. The fault current type and the grounding system, their interrelation. Please let me know if this is clear. I can move to the next concept, because this when we are coming on the fault current earthing, so we should have total understanding. That's why I have taken this slide. Okay, now so coming to the
Excuse me,
next.
please.
Yeah.
Sir, the story behind this is like as you concluded that in case of three-phase fault, there's no need of grounding in order to protect the system, right? It's not
Yeah.
mandatory for
Yes.
three-phase only, right?
Yes.
And for other cases, like unbalanced cases, there is a must to apply some groundings,
Yes.
be it neutral ground register or solid grounding or whatsoever.
Yes.
The story is what I guess is in case of three phase, the system is symmetric. Only positive sequence circuit we draw. Their neutral voltage is zero. It remains zero in case of balanced three phase fault.
Mhm.
But on the contrary, in case of unbalanced fault, there is a neutral voltage,
Mhm.
and that neutral voltage leads to this current.
Mhm.
That is why neutral grounding in case of unbalanced system is mandatory.
Mandatory.
Am I right?
Yeah, you correct. You are 100% is correct. Yes. And that is the reason we have taken this slide intensely, to understood the complete picture for the grounding, that if we are doing the grounding, if we are going to the solid grounding and GR grounding, so for what current we are discussing? Grounding for what current? For which type of the current? So not for the three-phase fault current. All things for the line to ground fault current.
Yeah, got it, sir.
Yeah, Mohammed Jan, I'll come on the earthing transformer. Yeah, you see, if you come on the earthing, I will cover each things, Mohammed Jan, and beyond your expectations. You don't worry about that. Earthing transformer, zigzag transformer. NGR is one statement. NGR, neutral grounding reactor, that we use in the shunt reactor, that we use in a line shunt reactor, that is used in 400 kilovoltage and above substations, not below. I'll come on that earthing transformer. Zigzag transformer. Their sizing calculations, their selections, these are one by one. Yeah. So let us conclude what we discussed so far. Let us conclude. Let us conclude. What is mean by earthing? This is clear to everyone. Equipment is standing for on its foundations. So already on the earth. So what is we are talking for the earthing? The earthing is connection of outer and closer metal body of equipment above the ground to a metal electrode pit that is below the ground by a metal strip, that is called the earthing. Metal to metal via metal strip called the earthing. Metal of metal strip may be copper, GS, MS, GI. Based on the client project specifications we can select. Earthing and difference, why earthing required difference between earthing and unearthed system, this also we have discussed, right? And then drawback of ungrounded system, here we have taken the second point of what is the drawback, that if we do not do the grounding, then we cannot sense neutral of transformer is ungrounded, then the line to ground fault could not be sensed. That is the drawback of the ungrounded system. And at time of line to ground fault, the phase voltage increase to the line voltage. This delta star earth. So if we take delta star ungrounded system, then line voltage jump to the phase voltage jump to the line voltage, fault current 0. If I just earth this neutral, then what will happen? We can sense the fault current, that is 6.543 kilo ampere, and the phase voltage remain as the phase voltage, it is not jumping. So this is why we provide the earthing or grounding for the neutral. We discuss here that the AC current and DC current which is dangerous. So as per this earthing standard IEEE 80 clause 5 and subclass 5.1, the human body can withstand 5 times more DC current compared to the AC current, which means that AC is more dangerous than DC current. How much current a 50 kg body weight and 70 kg body weight can bear, can tolerate? 50 kg 116 milliampere and the 70 kg 157 milliampere per 1 second. This is the phase of the relevant IEEE that we have taken. Okay, now type of the earthing we discuss: equipment earthing. First, system earthing. Second, and in system earthing, if we talk that system earthing, equipment self protections, the neutral point of generator or transformer is connected to the ground, and in that fault, three-phase fault point will not link with the neutral grounding or system. This will be remain same. This is the example that we have taken, right? Fault current for grounding. So, but the probability of three-phase fault current is very low, as we have discussed in the beginning. The most type of fault is line to ground fault, that is about 85% of total fault type. Therefore, all the discussion of earthing is for the line to ground fault type. Where the neutral or grounding transformer provide the return path for fault current towards the source or transformer through the grounding of neutral. We put the CT on the neutral to sense the line to ground fault by CT, and it send output to relay, and relay provides protections. Therefore, we can see that with help of neutral grounding, the line to ground fault can be sensed. This is the point. But if the neutral is not grounded, then it cannot be sensed, and system or tapo may damage. So this is the point. Here I have taken this one example. Delta star line ground fault happens. This is the return path flowing back toward the trafo. Here put the CT, and that giving output to the relay, and relay will give tripping command to this circuit breaker, and it will protect the trafo against the damage. Okay, so now again coming on a system earthing, as we have discussed that there is two type of earthing, system and equipment earthing. Now coming again on system earthing. So as discussed, the system earthing is for the equipment protections where the neutral point of generator or transformer is connected to the ground. Now this connection may be direct connections to the ground, as I have taken this snapshot from the site. Neutral bushing, you can see here This is my earthing conductor, and now this is going directly to the ground. There is no any intentional other equipment I have put. Only this direct connection to the ground. This type of the earthing we call as the solid grounding or effective grounding. So the system earthing may be direct connection to the ground. If direct connection to the ground, then called as solid grounding or effective grounding. But there is a problem with this, with the solid grounding, is that there is a huge or large current of single line to ground fault current. What I mean to say that as we can see here also, that at the time of the fault, let me take this example. Fault is line to ground, 7.26 km voltage current is flowing. So what is this disadvantage of this solid grounding, of this kind of the grounding, that a large amount of single line to ground fault current flow at event of line to ground fault, and approximate where the 85% fault type is line to ground fault. So huge amount of current is flowing. So therefore damage will be more because fault current is more. So in order to limit the damage, or in order to limit the large single line to ground fault current, there is resistive grounding method NGR introduced. And in electrical system grounding, this NGR we also use. So second type of the grounding, first is solid grounding, drawback large line to ground fault current. Next step grounding introduced, that is the NGR. In that NGR will limit the fault current. So system, but there is a drawback of NGR. Yeah, NGR can limit the fault current, but again there is a drawback of NGR. I think when we limit the fault current at any phase, in other remaining two phase voltage get increased. Due to this reason, the NGR method is not used for extra high voltage substations and used mostly for medium voltage and high voltage or HT applications. What I mean to say, if I take now, let me take this solid grounding. Let me take this one. Let me take input here. I have taken a transformer grounding delta star. In the grounding now I have taken the resistance type. If I took the resistance, this is my phase voltage, and now they will ask me, the ETAP will ask me that how much current I wanted to limit. So how to decide the limit current? That how much current I should allow to flow right now. This is also one point of discussion. This we should also understood, right? How much current we should allow to flow. Okay, at present I have taken suppose 100 ampere. So 100, based on this 100 ampere, they are telling this 63 ampere, 63 ohms NGR required. If I put the 63 ohm, how to calculate the NGR rating, I will come on this point also. Okay, how much current we should take, this I will come this point also, but just for the point of the comparison between the solid and NGR grounding, I am clicking on the OK. Now let us compare between solid grounding and the NGR grounding. If I select and let me do the line to ground fault, let me do the 60909, and then line to ground fault, let me run. What I can see here, how much current I wanted to limit, this is already clear. I wanted to limit 100 ampere only. So what will happen? What is happening here? Yeah. Okay, just give me 1 second. 60909 and 3-phase fault. Let me go to the line to ground fault and let me take the phase value, ABC value. R by B phase, just I wanted to take all the 3 phases in a common picture. All the 3 phases. Yeah, let us do a comparison between these two type of the grounding, solid grounding and the NGR grounding, and let us make some concept from here, right? I'm just doing comparison between these two type of the grounding. Let me take the snip from here, snipping tool, and I select it here and I can do the comparison now. Yeah, but I understood here, let us understood this result here. Delta star this trafo we have 10 MBA trafo rating, 10 MBA trafo here, 34.5 divided by 11 kilovolt is, that is my system here, right here, 34.5 divided by 11 kilovolt system here. And once I put the NGR, what was the drawback of the solid grounding? That at the time of the line to ground fault, there is a huge current flowing, as we can see, because we have taken line to ground fault, so the remaining two phase is healthy, so fault current is 0 kiloampere, right? And when the fault happens, suppose it is on the R phase, so R phase voltage comes to the 0, right? And the remaining Y and B phase healthy, so it is coming, voltage is coming 6.44 and 6.41 here, and the fault current on the healthy phase is 0. So I hope this solid grounding is clear. Now when it comes to the NGR grounding, what we can see that when I put the NGR, yes, fault current we can limit very well. 101 kiloampere means 100 ampere, that I wanted to limit. What is the drawback here? Drawback here, initially 6.44, now this jump to the 11 kilovolts, right? Am I correct? My phase voltage jump to the 11 kilovolts, right or not? As we can see through the simulation result also. Don't worry about how to handle the ETAP, how to do this short circuit analysis with the ETAP. At present, we are just making the concept with respect to the earthing or grounding, and for the ETAP we will discuss separately. Okay, in that we will do the manual calculations, manually fault current we will calculate and we will compare with the ETAP. That is a separate topic. That is chapter 5, we can say, in the syllabus. Chapter part 4, system study. Okay, now here just for the grounding, if I'm, because why I'm taking this example, if I'm telling some statement without result, like you can believe or you cannot believe, but here we have some study simulations result. What we can see here, with help of the NGR, yes, the fault current we have limited, but the phase voltage jump to the line voltage. So what will happen, that when the voltage is jump to the line voltage, in that case all the phase insulation we have to design for the 11 kilovoltage. All the equipment rating, all the LA rating, surge resistor rating, all the equipment rating, insulation requirement will increase, and then the cost of overall system will increase. Just to limit this current, I am increasing the overall system cost, right? So where we use NGR, where we should go with the solid grounding, the difference is clear, right? The difference is clear. Now where we go with the solid grounding, where we should go the NGR grounding. What is the selection? Due to this reason, NGR method is not used. Drawback of NGR earthing, like if my slide is not clear, you can see, I will zoom here. But drawback of NGR earthing, when we limit the fault current at any phase, in the other remaining two phase, voltage get increased. As we can see here, voltage get increased, right? Due to this reason, NGR method is not used for extra high voltage substations and used only for medium voltage and high tension applications. Now again, here is one sub clause here. I'll come on that topic later on. Because the higher voltage means the higher insulation requirement, so overall system cost will increase. Therefore, for the extra high voltage substations, we go for the solid grounding, as the equipment is already designed for the higher short circuit rating due to the grid requirement, and NGR use. So that is why, what is my statement here, that for the extra high voltage substation I will not take NGR grounding. I will always go with the solid grounding. Why solid grounding? Because my voltage remains the phase voltage, and since the current is flowing higher, but already I have taken the sufficient rating of the equipment. So, and there is no any rotating equipment, so there is no any drawback with this fault current. We can very well sense with help of the CT, with help of the relay, And as we know that in extra high voltage substation, my circuit breaker opening time is how much? My breaker opening time is how much for the extra high voltage substation? Breaker opening time, I hope you know what is the breaker opening time for the yeah, 33 kilovolt is always NGR, yeah, not always, but when the I'll come on the NGR, when NGR, when not NGR, yes, that is also we need to discuss for 33 kilovolt system. But yeah, what is the breaker opening time for the extra high voltage substation? Breaker opening time, not the breaker withstand time, Mohammed Chain.
So 2 millisecond.
Not 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 2 millisecond. I don't think 2 millisecond. Yeah, 50 to 80 milliseconds, correct. It is around 40 to 60 millisecond like this. Okay. Yes. Yeah. Since in my extra high voltage, my breaker, we use the unit protection. I will come again later on about what is the meaning of unit protections. But we can write here as a statement that in extra high voltage, we use the unit protections. We use the distance and differential protections for the equipment protections, and they operate instantaneously. They operate in 40 millisecond, 60 millisecond, around this range. So even though fault current is coming very much, but it will be, breaker will operate, the relay will operate instantaneously, breaker will operate into 40 milli 60 millisecond. The system will isolate very quickly, and that is not going to damage any equipment. But when it comes to the 33 kilo voltage, this LT and ST voltage, this medium voltage and ST voltage, here the we every time we do not use the unit protections, we use the overcurrent protections, we use the 50 overcurrent and earth fault protections, and the we do not use the unit protections in medium voltage times most of the time. In that case, the relaying time is higher due to the, because it is coordinated with the downstream relay. Relaying time, the relay operation time with respect to the relay coordination, it is higher, and breaker opening time is around 80 millisecond. So even though two statement here we deliver that relay will operate with higher time, and breaker will open the circuit in higher time. So this fault current will be, if persist in the system, it may damage to the equipment. So that is why when we comes on the medium voltage and high tension voltage, ST voltage, we wanted to limit this fault current with help of the NGR. I hope this statement, both is very important statement. I hope this is clear to everyone what I'm trying to stress. Why and solid grounding I take in the substation? I'm trying to explain this point. Why is solid grounding I take in substations? I am trying to explain this concept. Why NGR we take in medium voltage and high tension voltage? I was just explaining this concept. This is one reason. I'll come with other reason also. This is not the total reason, but this is the one reason and one important reason. Now, what will happen? Okay, so next next I can do one more statement. So this is the one statement, and like in 33 kilovoltage and 11 kilovoltage, when NGR is not required or when it is required, when it is mandatory that we have to put the NGR here, whenever this transformer is connected to a generator. What I mean to say, let me take one project example. Let me take one project example to explain this statement. To complete this statement, project. What is the project? Project for the power plant that we have executed. Yeah, where is that project? Power plant. Yeah, this is the one project. Yes. Here I have generator. Here after generator we have the GT, or we can say GSUT, generator step up transformer. And now here I have put the NGR. 600 ampere for 10 second. Okay. So what I mean to say, what I'm trying to say, this is the example of the thermal power plant. Whenever this transformer is connected with a one generator on the upper side, upper string, or if this transformer is connected with one rotating machine like motor. So whenever this trafo is connected with the generator, with the rotating machine like generator and the motor, in the rotating machine there is two element, two part we have. One is the winding, second is the core. Right now, core and winding we have in the rotating machine, but in static equipment like in substation we do not have like this core and winding here. But in generating, in rotating, in generator, in motor we have. Please concentrate here. This is very modest statement. What will happen when we have the winding, when we have the core in the rotating machine, and if this fault current, high fault current is flowing, if it is flowing through the winding, it is not an issue. We do not want it. We are not bothered with the winding, because winding we can do rewinding at the site. We have the rewinder, right? We have the rewinding saw, so we can do the rewinding. That is not the point of concern. The point of concern is that if this fault current travel in the core, and core have the insulation, and that insulation is very thick. It is very thinner insulation that we use inside the core, right? So due to this fault current, higher fault current, due to the higher fault current that flowing through the winding, it will generate the heat because we have the coil in the winding. Due to this heat, the core insulation may damage. If the core insulation is damaging, then you cannot fix the core insulation at the site or in your rewinding shop. You have to send back to this motor or is this generator to the manufacturing company. Now they will again do the core. They will again make the core insulations, the winding, rewinding, all these things, and it will take more time, around maybe 2 or 3 months. And if you're taking this machine, this motor from China, then it is again going to take more time, right? So, and your process industry is stopped. So whenever we have the rotating machine, in that case we cannot allow to flow this much short circuit current. In order, why? In order to protect the core of the rotating machine, core insulation, in order to protect the core insulations, we cannot allow this current. In that case, it is mandatory to use the NGR. Point number one is this. Second point, we have to use the NGR type system earthing we have to use here. Second point, how much current I wanted to allow here, or how much ohm we wanted to put here. So the allowable current I have taken 100 ampere here, but this current, how much allowable current through NGR, this allowable current we have to.
Sir, 1 minute. That only skipping to only visible. The screen not visible.
I am not moving my screen. My this dot is visible or not?
No, sir.
Oh, let me check with that. I am not moving my screen. Yeah, my screen is visible.
The screen is visible, sir.
Yeah, Bharti, you check at your end. Yeah, this is visible for others.
Yes. Screen is visible, but dot is not full.
I'm not moving my screen. Yeah, my screen is fixed. I'm not moving. I'm just explaining on this screen only.
Yeah, okay, now.
Okay. So second point of concern here, that how much current that we allow to flow through the NGR. For that we have to discuss with the equipment, with the rotating equipment manufacturer, that how much current their stator, their core can withstand without damage, and for that the equipment vendor supplier provide one graph. In that graph they provide that how much current they can their core can withstand without damage. So my NGR current should be less than that core withstand rating. Point number one is this. Point number two, if you are not able to get these information from the vendor, then how much current I can put here? In that case, my allowable current, I can take max to max my full load phase current, because my full load phase current, suppose this is 400 ampere or 500 ampere, it is flowing in the motor or the generator, and the core is not damaging. It means this much current can core withstand. So my NGR here, I will take the current equal to the full load current of the motor or the generator. Here I explain two important concepts. Concept number one, here I discussed how to select the NG, how much current, how to select the current, that how much current we wanted to allow to flow. Like in ETAP also we have to put this current, then it will give the ohm, right? And so this, how to decide this current, there's two concept. Concept number one, we can discuss with the vendor that how much current their core can withstand. Based on that, this current we take, and we wanted to keep this current less than their core withstand capacity. Or if it is not available with the, you cannot get this information from the vendor, then take this current max to max your full load current of the generator or the transformer, not more than this. I think my both statement is clear. How much current for the NGR? Why NGR? This is clear, right? Why NGR? How much current through the NGR? How much resistance? I will come on this also, but this two statement is clear or not? Please let me know if it is clear or not, because these are point.
Excuse me, sir. I have a clarification. This is with regards to the where the NGR is supposed to be used. So you said that mostly it will be used in rotating machine, in the places where you have rotating machines due to the concern for the core. Why is it that is it not a concern for the transformer also? Because transformer is also having the core, and it may also get damaged if you don't use the NGR
See,
in lower voltage sensing.
see, actually, what type of the material that we use in the in the transformer? This is not the same as in we use in the motor, right? That we use, what type of the core we use? That is the CRGU, cold round grain oriented, right? Now, type of the metal is different in the motor and the generator winding. Raghunath, you have raised this point.
Yes, sir. Yes, sir. I'm just noting it down because I was not. I'm not. As I told, I'm not aware. So I was having this clarification.
Yeah, don't worry. Yeah, you will get this. Yeah, due to the different materials now that we use in the transfer, the different material, and that we use in the motor, that is a different material. So the trafo, they are considering this much particle, but when it comes to the motor and trafo, we use the CRGO type material for the core. When it comes to the motor and generator, it's not the same. So that is the reason. If you wanted to limit, you can limit. There is no problem. This is your choice. But that is the reason that we are not putting, because we wanted to have the sufficient fault current. That is why, so that we can sense the fault current, actual fault current, and we have the instruction of CRGO that is not same as the motor. That is why.
Sir, there is a doubt.
Yeah.
Sir, do we use NGR in our distribution transformer, feeding power to our distribution? I mean, this domestic house appliances.
Yeah, like in the distribution substation.
Yeah, distribution substation like 6.6 kV or lower voltages.
Have you seen any NGR?
Sir, one of the substation near to my home, they have installed NGR. Though I'm not exact, I do not have exact clarity what exactly is the resistance value, but they have their NGR value connected to the transformer.
In the distribution substation.
Yeah. Though it's feeding power to some pumps. That substation is
Yeah,
actually
that
made
is the reason, because
pumps.
they are feeding the power to the pump, right? We
Okay.
know that was the reason.
So can we conclude it as if that
Yeah, the conclusion is
NGR
that,
is yeah,
yeah,
yeah, please
yes, yes,
please
yeah,
please go
you
on the question.
conclude, as per your understanding. I will add.
Uh, sure, sir. Uh, like NGR is needed where we have first of all generator transformer.
Yeah,
So there we need
GT.
an NGR
So GT here we needed
at
the NGR.
generating station.
Yeah, generating power plant, right here we needed the NGR, and NGR we need it when we have when there is any motor, that there is any transformer, and this
Yeah,
transformer is feeding to a bus bar, and that bus bar is connected directly to our motor.
right, sir.
So here NGR.
Yeah. Or
Yes.
other way, we can use NGR for distribution transformer, or for that matters, any sort of LV or medium voltage transformers
If
which are feeding power to motors or
pump.
inductive load.
Yes, yes. In that case, yeah,
Okay.
rotating equipment, any motor pump in that case.
Okay.
And otherwise, other than this NGR is not mandatory requirement. It is not a mandatory requirement. Okay, as a design engineer, you should go NGR with two places. For other cases, it is not the mandatory required, because if there is no any rotating machine, there is no any winding, there is no any core, there is no any insulation of the core. So what will damage? Because there is no, if no any rotating machine, nothing, right? So in that case, we can avoid the NGR, but in this case, we have to consider the NGR. We cannot avoid. Okay.
So one more thing, like you said, that NGR rating, like the maximum allowable current of NGR, could be equal to phase current.
Two concept here I discussed. Two concept for the NGR current. How much current I wanted to allow. First, how much this core of the generator. Let me put here one generator also. Generator, because generator have their winding and their core. So how much the current, how much the core can withstand. So this allowable current value should be less than this current, this withstand current of the core. This is the one. Suppose if you are not aware about the core current withstand capacity, and now you have to design this grounding. In that case, because this current is flowing, the phase current is flowing in the motor, it means the motor can withstand this much phase current what is flowing through the core, can withstand, right, without damage.
Hmm.
And that is what is working right now.
Yes, yes.
So in that case, the max to max current that I can take, max to max current, that is my phase current, or below the phase current, this is fine, but not more than phase current.
Okay. That means NGR value could be different depending upon what is what 2%, like suppose 2% are calculating the value of resistance, I mean NGR resistance, then they may have different values.
Correct. They may have different value based on the how much current they wanted to limit.
And this may also depend upon the CT ratio which is connected to the neutral, right?
This
For
do not
protection system.
go on the CT ratio, because CT I will decide that how much CT I wanted to put. First of all I have to put the NGR, then we will go on the CT.
Okay.
So the NGR value will be different. It depends on the how much current I wanted to limit. How to calculate this NGR value? Here we have some formula also. Yes, this is this page. This resistance V is equals to IF. How much current we wanted to allow? What I mean to say, that suppose my phase 11 kilovolt is my line voltage. We convert this 11 kilovolts into the phase voltage. Then we have to divide by √3, right? This is how we decide the NGR neutral grounding resistance, the ohm value of this NGR. My phase value here, and now how much current I wanted to limit, 100 or 200 or 300. So first of all, before doing the NGR calculations, we should know that how much current I wanted to limit, and this current I will put here in my ETAP. In my ETAP, I have taken the 63.5 ohms because my voltage is 11 kilovoltage, right? As you can see here, this is 11 kilovoltage here, 11 kilovoltage here. So when I divide this 11 kilovoltage by root 3, it will come 6.35 ohm, and again this is 6.35 kilovoltage kV. Again I divide by 100 because I wanted to limit 100 ohm, sorry, 100 ampere. 0.635 multiplied by 1000 because I wanted to convert into kV into voltage, so multiply by 1000. 63.5 ohm coming, and that I have, that ETAP is automatically calculated here. But if I change my I to 50, then this will be 120 right now. If I change the 200, then it will be 31. So first of all, we should know that how much current I wanted to allow to flow through the NGR. Based on that, we decide the impedance of the NGR, our neutral ground NGR rating. Based on that, we decide. So hope this point is clear, that how much current we can, this is what we discussed. This current, two value, one is the maximum core withstand capacity based on the graph, or if not clear to us, then this value should not be more than the phase full load current of the generator or full load current of the trough. Suppose this is 100 ampere flowing 200 ampere is my full load current of the motor. I can say that yes, this 200 ampere this motor can withstand. If 200 ampere fault current is flowing, it means the core will not damage, right? I can say like this. I can assume like this right now, Abhinav.
Right, sir. Absolutely.
I can, like, if I took 200 ampere, and if my client is asking me to explain why you have taken 200 ampere, I can explain in this manner.
Yes, sir. Definitely.
Considering this 200 ampere is the full load current, means core is designed for 200 ampere. So I limited my full fault current to 200 ampere, and to limit the fault current to 200 ampere, I calculate my NGR rating as this right now.
Right, sir. Right, sir.
This is what. So here we discuss the NGR sizing calculations. Here we discuss that how much current we should allow to flow, and what is the basis of that current selection. Yeah, NGR design based on that or not? Yeah, we are discussing NGR design based on the fault current, how much current you wanted to allow to flow through the NGR. Okay, right? 2CT, one is the REF, second the SEF. Bharti, restrictive earth fault and standby earth fault. 2CT1, yeah, CT1 core 2. Okay, not say 2CT. You say 2 core, Bharti, not the 1 core. 2CT like this. Okay, I'm clear with this NGR system grounding, clear system grounding. Now let us do the one. Conclude this discussion with the comparison. Thereafter we do the conclusion. Solidly grounded system, the extensive flow of ground fault current enable accurate detection and location of ground fault. That is the advantage of solid grounded system. Disadvantage, it permit third harmony because it permit the line to ground fault, means it permit the zero sequence current. It means it permit the third harmonic current and the multiple of third harmonic current, the zero sequence current. This is one disadvantage. And the third harmonic and multiple third harmonic is more dangerous for the rotating equipment, not the static equipment. Ground fault current magnitude is high. The core damage at the point of fault in rotating machine like generator and motor will be high due to the high fault current. In substation, all the equipment is static equipment, so solid grounding is okay for the substation. Right? Advantage, disadvantage for the solid grounding system. The resistor grounding system advantage. The resistance grounding limit the fault current to avoid core damage. In rotating machines, winding damage is tolerable, but core damage is not tolerable. Next advantage, reduce the burning and melting in electrical equipment. Next advantage, reduce the mechanical stress compared to the solid grounding system. Reduce the restrike or arcing fault compared to the ungrounded system. Ungrounded system, not solid grounding system. But disadvantage, by NGR, when we limit the fault current at any phase, in the other remaining two phase, remaining healthy two phase voltage get increased. That we have seen here. So that is the disadvantage for the NGR. Okay, so now this NGR again divided into two parts. For this, our grounding resistance grounding system divided in two types: the low resistance grounding and the high resistance grounding. Low resistance grounding, if in that we limit the current about 100 to 800 ampere, and in the high resistance grounding we limit 10 to 15 ampere current. So we have to select that how much current we wanted to limit based on my core resistant capacity. The fault current value selected based on rotating machine core resistant capacity value provided by the equipment manufacturer. This is what we discuss. NGR calculations, already we have discussed the NGR calculations. The fault current should be keep in mind while deciding the NGR. On the NGR value, too high a value of NGR would limit the current to a very low value, which will not be able to activate the earth fault protection. So we cannot keep NGR value too much high. So in general, we allow current in range of 100 to around 800 ampere. Now let's consider the maximum fault current flow through the NGR, and resistance is 100 ampere. So if 100 ampere, so we can derive the NGR rating as 63.5 ohm. The current carrying capacity of the resistance is 100 ampere, and the system voltage 11 kilovolts. The phase to ground voltage 11 by root 3, and apply the ohm law. We can get the resistance value of the NGR. This is how we can clear we can find the NGR. Same we have taken here. This star winding we have taken here. This fault is the ground fault happens. Here we put the NGR, return path of the ground, and this NGR value 63.5 ohm we can put here. This is one calculations that we do for any project submission. Like this is the thumb rule. This is the format of the calculation that we have to do. NGR sizing calculations, like steps that we perform. Okay, and I'll come later on about this. So a lot of things we have for the grounding, and I don't think that this is possible to complete in one session. So a lot of things like again, effect of grounding on short circuit current, NGT, because what will happen in the NGR is a drawback that when we limit the fault current very much, reduce the fault current, the NGR, this NGR will heat up. So heat is one problem with the NGR. So we have to think alternative of the NGR, right? So this we have to go on the NGT neutral grounding transformer, earthing and zigzag that we take. Okay, so alternative of, and second, if system is delta connected system, then how we can convert this ungrounded three-phase system to the grounded three-phase system. So that for that we have to use the grounding transformer. So these a lot of things, zigzag introductions we need to discuss. So it's not possible to complete in one class. So we'll keep the next session, the remaining session, in the next class, right? So far what we discussed, let us conclude today's session. What is total discussion that we have done? Why, like difference between earthing and grounding that we discussed. Then what is the earthing that we discussed? Type of the earthing that we discussed. Like if ungrounded system, so what is the drawback? And the current, what comes when we talk about the grounding or earthing, or grounding particularly we can say. So the current is the line to ground fault current. We discussed that how much current a person can tolerate, the tolerable body current IB, that 116 milliampere, 157 milliampere that we discussed. AC is dangerous, that we discussed which one is dangerous. Then type of earthing we discussed the solid earthing, we discussed the NGR earthing, and we done some comparison between the solid and NGR earthing, and we calculated the NGR value based on that how much current we wanted to allow, that we discussed. Now in the next session we'll discuss the remaining part, NGR, this calculations, and then we'll go on this delta winding transformer, and then we will discuss about the grounding transformer. These all, and their selection, their sizing calculations as well. Okay, if any query, let me know. I'll discuss for that.
Sir, this is Arva Srinivasan.
And 1 second, sir. Arvind, your point is correct. 400 kV shunt reactor connected with the NGR. This point is very 100% correct. 400 kV shunt reactor. There's two type of shunt reactor we use, Arvind. One is the bus shunt reactor, second is the line shunt reactor. Bus shunt reactor not connect with the NGR. But when it comes to the line shunt reactor, the line reactor will connect with the NGR. Okay, Arvind, I hope you have seen the line reactor where the NGR is connected at the site. Right, Arvind, are you there? If you are there, please let me know. We can discuss more on that. Okay, I'll take this point in the class. I will discuss about this NGR.
Sir,
Yeah, it is
I
connected
don't know.
in the line side. Yes, Arvind. I was telling that it is connected in the line
yes,
side,
sir. Yes, sir.
not in the bus side. So can you tell me that why not the bus side and why it is required at the line side? What is the concept? Did you ask? Did you ask that substation engineer that why NGR coming here? If yes, then fine. If no, don't worry. I will explain why NGR required in the line shunt reactor. Why required in the line shunt reactor? Why it is not required in the bus shunt reactor? And I can tell you as of now, this NGR is required to enable the single phase auto reclosing, the SPAR. The NGR enables for the auto reclosing. Okay, Arvind, I will explain here in the next in the earthing module that why it is not required in the bus shunt reactor. Yeah. Yes, Srinivasan, now please come.
Sir, this NGR design based on transformer capacity.
No, Srinivasan, that NGR based on the fault current.
Okay, but
Not the
okay,
fault
sir.
current, basically how much current you wanted to allow.
Okay, sir.
I don't worry,
Could
Srinivasan,
you,
I have one slide for the NGR calculation.
yes, sir. Another small information. We have 5 MVA transformer. There is a NGR. Okay,
Okay.
but 2.5 MVA also is there. We have, but 2.5 MVA we don't have NGR system. That's why I asked based on capacity or what.
So when you talk about the NGR, as we discussed with the, we know that 2 point we have to see that uh, what kind of the load current on that transformer, right? I hope that on the 5 MVA load there might be some rotating machines. The HT motor or MV motor they have put on that transformer bus bar, right? And second point that how to calculate the NGR, it not depends on the top rating. It will depend that how much current we wanted to allow to flow. Okay, Srinivasan.
Okay, clear.
And don't worry, in the next class I will start from the NGR calculations again.
Yes, clear.
But the value is the same what we discussed today. Only we will convert into a systematic pattern. That is the thing. So next class, what we are going to discuss? Let us discuss NGR sizing calculations. This is the one. Then jig-jag transformer that we use. Jig-jag transformer we use. Or earthing transformer we use. So their selection and the calculations. Right. This we will discuss. NGR calculation that we will discuss. Even though we have discussed today also through the e-tab, but how to like put in a document that also we discuss. NGR zigzag transform are earthing transform calculations and the selections. And then there is one another type of NGR. This is called as the neutral grounding. This is the resistance, but this is the reactor R NGR, and that we use with help of in extra high voltage substation. I can say the ultra high voltage substation that we use in 400 kilo voltage and above substations, not below than this. And this is used in between the shunt reactor and the ground we use this NGR in order to allow the single pole auto reclosing SPAR. We'll discuss about this topic concept also, right? And thereafter we'll go to the substation grounding calculations. We discuss about the earthing pit, what the distance between required between two earthing pit, the minimum distance, how much required, and the drawback of the NGR, like there is heat problem with the NGR, so alternative of NGR, how to convert any ungrounded system into the grounded system, or I mean to say how to convert, how to achieve the grounding in a delta connected transformer. My trafo is if delta. Here we have the star and this is my delta. Let me take this into in this. If I run the fault current in delta connected system, if I run the line to ground fault current, you can see if my winding is delta, my fault current here coming, right, 100 ampere, here coming 7.26 kiloampere, but here 0 kilovolt, 0 kiloampere coming. So how to sense that fault current when the trafo is delta winding, that also we'll discuss in the next session. Okay, any doubt, any query from the today session? Anyone, let me know. Yeah, Abhinav, Anand sir, about you, and hers for then. Yeah, Srinivasan, what about you?
Yes, yes, sir. I have last inquiry.
Yeah.
Today I joined first class. I have
See, what I
I
will do
have
is, Srinivasan, with you, that I will take you in this batch, and my next batch when I will start, I will inform you. You can start again from beginning.
yes, agree, sir. Last inquiry. This presentation and slides after module complete after, is any possible send the by mail?
I'll confirm you later on. Yeah,
Yes, sir.
I will confirm. I will confirm. Let me check.
Yes, because this is well useful for
The recording we
again
used to
learning.
share. The recording we used to share. Okay, Srinivasan, I will confirm and come back.
Okay, sir. Okay, sir.
Okay. And the Kamesh, what about you?
Can you hear me? Can you hear me?
Yeah, I can hear you.
Hello? Yeah, no, it is very interesting. What I would like to do is I will call you. It's a little bit late for you, isn't it? So I will call you after the class, and I will
Okay,
just
okay,
have
okay, sure, Kamesh.
Okay,
Okay,
it is very interesting. I really enjoyed it.
okay,
Some of the stuff I have already done it, but yeah, I will catch up with you later. Okay?
okay. Thank you.
Thank you.
Thanks.
Thank you.
Yeah.
Really appreciate for your time.
Okay, okay. So thanks all. Thanks for your attendance. Thanks for the join.
Yes, thank you, sir.
Hello, sir.
Yeah, Raghunath, I will share with you recording. You just text me. I will share you the recording. You don't miss any part. Okay. That I can confirm you at present. Yeah.
Hello, Raghu, sir. I have one small doubt, sir.
Yes, sir.
Sir, you have told that in Sri Lanka, I have faced one practical example that soil resistivity is more in Sri Lanka.
Yeah.
That for reducing soil resistivity, we can increase the impedance of transformer, sir, or else we can lay the cables so that we can use fault current for line to line also.
Yes, we can do Hertzbergen, and don't worry. After my earthing calculations, I will tell some corrective action.
Okay.
That if
Okay.
what is the problem and what is the solution.
Okay. Sir, and one more thing, for NCT transformer, we are using the what is the ratio of CT we are using for the same phase size CT. Means if in phase side it is a 2000 means we are using in NCT also 2000 amps.
Yes, we
But
can
in
do. We can do.
but in NGR we are using only for 600 by 1 CT, sir. Why like that, sir?
See, Harshvardhan, I'm not telling the CT sizing now. I'm telling just 600 is like one example.
Okay, okay.
This is not the CT sizing. There is a separate topic.
No, I am not asking about CT sizing, sir. But for NCT also we can use 600 by 1 amps, sir. That is the thing I am asking.
For the NGR type, you are telling for the NGR also.
For NGR we are using 600 by 1 amps in CT, sir. For NCT also we can use 600 by 1 amps, sir.
For the solid grounding.
Yes, yes, yes.
Yes, for the solid grounding, yes, we can use.
Sir, one more thing you have to tell that for normal human body, he can withstand 116 amps for if he weight for 50 kgs, he can withstand 116 milliamps like that you have told, sir.
Yeah, for 1 second.
But it depends upon the resistance, sir. Whether a body is in wet condition or dry condition,
50
Yeah,
kg,
for
then
that,
then
for
not like.
yeah, I understood your point. Also. For that, it depend. The resistance depend on the voltage. That how much voltage a body can
Yes, sir.
tolerate.
That is the thing I get also. Why? Because if we 50 kg or 70 kg, suppose that the body is in wet condition means for minimum current also you get electrocution, sir. That's
Yes,
it.
yes, yes. Wait, you are telling the dry and wet conditions, right?
Yeah, yeah. Okay, okay, okay.
Yes.
Okay, sir. Thank you so much, sir.
Okay, okay. And Harshvardhan, if any point not clear, we are here with you. Okay, we are, because this take around 3 to 4 months. So many classes, many discussions we will done. So you can discuss anytime.
Okay, sir. Okay.
Okay. Yeah. Thank you. Thanks all for
Thank you so much, sir.
yeah. Thanks for the attendance. Thanks for the joining us. Okay.
Thank you so much, sir. Thank you.
Thank
It
you,
was
sir.
very
Thank you so
informative.
much.
Yes. Yes.